In this video, we are going to be looking at the various atomic models and what they predict versus what should actually happen. So let's start with our experiment. What really happens? The idea here is in this box we have some atoms. I'm going to turn on the spectrometer so it'll keep track for us what photons are emitted from the box as we go. And I'm going to turn on our light source and bombard our box of hydrogen with photons. The photons right now are set to be white, meaning all colors, and if you watch, there are photons that are kicked out at other directions. So there goes a red one, there goes a UV one, and each time one of those is kicked out, you get a mark down here, which is building up what the emission spectrum of hydrogen is. There's a line in the red, a line in kind of the aqua blue colors. There's a bunch in the UV, and if we wait long enough, we will get a couple of others as well. So I'm just going to take a minute and let you guys watch as this builds up. We now have a line appearing in the IR. And there is the line in the deep purple that is appearing. That one is maybe visible to you, maybe not, depends on your eyes. I think at this point you probably have the idea of what actually is seen. So now let's go look at the atomic models and what they predict. Original model is we had a billiard ball, and the idea here is that it's the protons, it's the electrons, it's the neutrons, it's everything, and if a photon happens to hit it, it bounces off. And so you get in your spectrometer just a nice white spectrum. Everything bounces, so it's not even keeping track, if you will. This was disproved with the discovery that you could actually break the atom apart. So now we have to go to plum pudding so we can add in our electrons. When a photon hits the electron in the plum pudding, it causes the electron to oscillate, and when it stops oscillating, if you look, it spits out a photon, but that photon is always in the UV. I'm not going to let this one go too long because it's doing exactly what it's going to do for the entire time. Now let's go look at the classical solar system model. This is what Rutherford proposed, and remember we discussed in the rest of the unit how this was unstable. Kaboom. No atom. So fundamentally flawed model. He knew it, completely knew it, but he said, hey, it's a good starting spot, so let's just put it out there. And then Bohr came along and he said, I don't know why, but if you make these assumptions, you get stability, and not only do you get stability, but you can actually get out the correct spectrum for hydrogen. So if you watch, when the electron is hit by a photon, it bounces to a higher level, and depending on what color that photon is determines what level it bounces to. And then when it decays back down to a different level, it emits a photon of the color determined by the difference in those energy levels. So you can see we're getting our lines in the UV like we got in real life. Here's the line in the deep purple, which I said maybe you could see. There is a line in the blue, which I don't think we waited long enough on the other one for it to come up. Here's the line in the red. And remember, there should be some lines out here in the IR as well. But there's one of them. There's some more. Right. It's accurately predicting where the lines for the hydrogen atom should be. Ah, there comes the line in the kind of tealy blue that we saw before. One other feature, notice it's telling you what level the electron is at any time. You can also look at it as an energy level diagram. Here it's bouncing up to n equals 3, down into n equals 1, up to n equals 6, to n equals 3, to n equals 1. When it emits a photon in a color that you can see, it shows what color it is. So we just saw one a minute ago that went from n equals 3 to n equals 2 in red. There was one that went from n equals 5 to n equals 2. That was in the blue. This is where we stopped in the unit. But I think it's worthwhile just doing the last two really quick. Along the way, we had Planck and Einstein saying, hey, look, energy is quantized for the photon and for the atom, or for the atomic oscillator that went into making the black body spectrum. De Broglie said, well, hey, if what Planck has said is true, that the particle in the atom has a frequency, then why can't it have a wavelength? And so instead of getting just the electron orbiting, it now becomes something that looks like it's oscillating, and it has a very nice wavelength and frequency associated with it. And it does the spectrum out that exactly what you'd expect. And then came Schrodinger, and he said, well, yes, but with quantum mechanics, there's all these weird features that mean you can't specify where something is as accurately as, hey, it's in this wobbly orbit thing. And therefore we get not orbits, we get these clouds. So it's higher probability that the electron will be where it is bright and lower probability for where it is dark. And the structure of the cloud depends on what orbit you're in.